So, that is what we are going to do now. So, let us in the general case. So, in general the set E, which is Lebesgue measurable, may not have a finite Lebesgue measure, but the Lebesgue measure being sigma finite, we can write E as a disjoint union of sets E j, j equal to 1 to infinity, such that lambda of each E j is finite. It is a measurable set and it is finite. So, now by the earlier case, because lambda star of E j is finite. So, for fix epsilon bigger than 0, there exists open set, call it G j, which includes E j such that lambda star of G j minus the set E j is less than the small number epsilon, but we are going to write less than epsilon to the power 2 to the power j. And you will see soon why we are doing that, because for each piece we are going to make it small and we are going to add up these pieces. So, now define the set G epsilon to be equal to union of G j, j equal to 1 to infinity. So, then G j is open. So, it is an open set, because it is a countable union of open sets G j's, and G epsilon includes G j includes E j. So, includes union of E j's, which is equal to E. So, it is an open set which includes E. Now, let us look at the difference further. So, let us observe further that G epsilon minus E, what is that equal to? That is union of G j's minus union of E j's, right. That is the definition, that is how we constructed. And now, here it is a simple set theoretic property, namely that this is a subset of union j equal to 1 to infinity G j minus E j. So, this is a simple set theoretic that union of G j's minus union of E j's is a subset of union of G j minus E j. And once that is verified, which is easy to verify, we get that lambda star of G epsilon minus E is less than or equal to sigma j equal to 1 to infinity lambda star of G j minus E j, which by our choice is less than epsilon to the power j. So, this is less than or equal to summation j equal to 1 to infinity epsilon by 2 to the power j, which is equal to epsilon. So, that proves the second property completely in the general case also. So, hence what we have shown is that 1 implies 2. Namely, if E is Lebesgue measurable, then I can find, given epsilon, we can find a open set G epsilon such that the outer measure of this is small, is less than epsilon. So, now let us go to the second step of the verification. So, we have verified the first step, namely 1 implies 2. Now, let us verify that 2 implies 3. So, let us assume 2 holds. So, 2 implies 3. So, we are given a set E. So, given 2 means let E be a subset of real line such that for every epsilon bigger than 0, there exists a open set G epsilon, which includes E and lambda star of E is just a set. So, we can't write lambda now, it is lambda star of G epsilon minus E is less than epsilon. So, that is what is given to us. and we have to construct a set say that the difference has got measure Lebesgue measure 0. So, the obvious way is make this epsilon small and small. So, in particular, so that says for every epsilon equal to 1 by n, there exists G n including E, G n open such that lambda star of G n minus E is less than 1 by n. So, we have specialized this given condition for each epsilon equal to 1 by n, and we got an open set G n which includes E. And now, because we want it smallest, so we want to let this become smaller and smaller. So, it says the following. So, define G equal to intersection of G n equal to 1 to infinity. So, what is G? G is intersection of open sets. So, note G is what is called a G delta set. So, a G delta set is by definition an intersection of open sets, and this set G includes E, because each G n includes E. So, G also includes E. Further, lambda star of G minus E, note G minus E is a subset of G n minus E, because G is the intersection. So, G minus E is a subset of G n minus E. So, by countable by monotone property, lambda star of G minus E is less than lambda star of G n minus E, which is less than 1 by n. So, lambda star of G minus E is less than 1 by n for every n. So, that implies the fact that lambda star of G minus E is equal to 0. So, hence we have shown 2 implies 3. And now, let us conclude the proof by showing. So, let us show we show that 3 implies 1. So, what is 3? So, 3 says that by 3. So, 3 implies that for E a subset of R, there exists open set G, there exists not an open set, there exists a G delta set G including E and lambda star of G minus E equal to 0. So, here is the set E, that is the set E inside, and this is the set G which covers it. So, that the remaining part has got measure 0. But note what is E? E is same as you take the set G, this is the full set, and intersect it with the complement of the outer portion. So, this is the complement. Look at the complement of this. So, intersection G minus E complement. So, this is a simple observation, because what is G minus E complement? So, this inside portion is right. So, let me just draw a picture again. So, this is inside is E and outside is G. So, this shaded portion is G minus. So, what is complement? Complement is the outside portion here and E. So, when you intersect it with G, you get E. So, E is nothing but G intersection G minus E complement, and this is a G delta set, and a G delta set is a intersection of open sets. So, this set belongs to B R, and hence this set also belongs to L. So, it is Lebesgue measurable, and this set G minus E has got outer measure 0. So, G minus E belongs to is a Lebesgue measurable set, because all sets of outer measure 0 are Lebesgue measurable. So, this set also belongs to L, and So, intersection of two Lebesgue measurable sets is Lebesgue measurable. So, this implies that E belongs to L. So, 3 implies, so this implies 1. So, this proves completely the fact that the 3 properties that E is Lebesgue measurable is equivalent to saying for every epsilon bigger than 0, there is an open set G epsilon such that E is a subset of G epsilon and lambda star of G epsilon minus C. The difference is outer measure small, and that is equivalent to saying that for the set E there exists a G delta set covering it such that the difference has got measure 0. So, this gives us a characterization of Lebesgue measurable sets in terms of open subsets of a real line. A corresponding characterization of Lebesgue measurable sets is obtained in terms of closed sets. Let us state that also and prove it. So, let us look at the next that for any set E in R, the following is true, namely E is Lebesgue measurable is equivalent to saying for every epsilon bigger than 0. Now, there exists a closed set inside E such that Lebesgue measure of the difference is small, and that is equivalent to saying that there is a F sigma set. So, what is a F sigma set? A F sigma set is nothing but a set which can be expressed as a countable union of closed sets such that. So, there is an F sigma set F inside E such that lambda star of E minus F is equal to 0. So, let us quickly prove this, and this will use the earlier characterization. So, let us suppose one holds E belongs to Lebesgue measurable sets. Now, E belongs to Lebesgue measurable sets implies there is an open set which covers E with difference of measure small, but we want closed sets. So, let us observe E belongs to L also implies that E complement belongs to L, right, because this Lebesgue measurable sets is a sigma algebra. So, if E is Lebesgue measurable, complement also measurable. So, this implies by just now what we proved. So, E complement is Lebesgue measurable. So, for every epsilon bigger than 0, there exists an open set G epsilon such that this includes E, and outer Lebesgue measure of G epsilon minus E is less than epsilon, right. This is just now we proved this fact, but so this is of E complement. We are applying the previous just now proved result for E complement, and now. So, if E complement is inside G, that means E will be including G epsilon complement, and note G epsilon is an open set. So, its complement is a closed set. So, let us call it as C epsilon. So, C epsilon is closed, it includes E, and we want to find what is the Lebesgue outer measure of E minus C epsilon. So, what is that? That is E intersection. What is this? This is just C epsilon complement by set theory, and that is same as E intersection. This is G epsilon. Oh, sorry, we want E complement. We want to find out what is the difference between the closed set inside E complement. So, that is sorry, not the complement E. So, E minus C epsilon is E intersection C epsilon complement, and C epsilon complement is nothing but G epsilon G epsilon. So, this is G epsilon intersection E. So, we want to conclude. So, now note that Lebesgue outer measure of E complement. So, Lebesgue measure of we had E minus. So, what is this? So, this we can also write it as G epsilon minus E complement, right, because E complement will be E. So, E minus C epsilon C epsilon is same as outer measure of G epsilon minus E complement, and that is less than epsilon. So, what we have shown, if E is Lebesgue measurable, then there is a closed set inside it such that the outer measure is less than epsilon. So, implies 2 holds. So, 1 implies 2 we have proved, and here we have just used the fact that a set is open if and only if its complement is closed, and applied the previous criteria. So, 1 implies 2 we have proved. Let us look at 2 implies 3, and that is once again for every epsilon what is given, that there exists a closed set C epsilon closed inside E, C epsilon closed with the property that outer measure of E minus C epsilon is less than epsilon. So, in particular for every epsilon equal to 1 by n, there exists a set C n which is inside E, C n closed such that Lebesgue measure of E minus C n is less than 1 by n. So, technique is same. So, put C equal to union of these sets C n. So, this 1 to infinity. So, this is a F sigma set, because it is a union of countable union of closed sets, and each C n is inside E. So, this set C is also inside E with the property that lambda star of E minus C. C is the union of all the C n's. So, if I take only one of them, C will be a subset of E minus C will be a subset of that. So, it is less than or equal to lambda star of E minus C n, which is less than 1 by n. So, implying lambda star of E minus C is equal to 0, and that proves hence 3 holds. So, given for every epsilon there is a closed set inside it, we have shown there is a closed set inside E with difference, there is not a closed set, a F sigma set with the measure 0. And finally, let us put that prove that 3 implies 1. So, E is a subset of real line, E is a subset of real line with the property that there exists a F sigma set C contained in E with the property that lambda star of E minus C is equal to 0. So, here is the set E, and I have got a set C inside it. So, this is the set C inside it, such that the difference has got measure 0. But now, note the set E can be written as C union E minus C, right. So, this is this portion outside and union the inside portion, and this is a F sigma set. So, it is a Borel set, and hence it belongs to is a Lebesgue measurable set. The set E minus C is a set of measure 0. So, that is a Lebesgue measurable set. So, E is a union of 2 Lebesgue measurable sets. So, implies 1, that is E is Lebesgue measurable set. So, we have proved the third property, namely 2 implies 3, and now we have just now proved 3 implies 1. So, the Lebesgue measurable sets are very nicely connected with topological nice sets, namely open sets and closed sets. So, for every Lebesgue measurable set can be covered by an open set, such that the difference has got Lebesgue measure small, and which is equivalent to saying a set is Lebesgue measurable. That is also a characterization. And similarly, a set E is Lebesgue measurable if and only if we can find a closed set inside it, such that the difference has got measure small. So, Lebesgue measure is a very nice measure on the real line, and it is defined on all Lebesgue measurable sets. So, in particular it is defined for all Borel sets, and it is translation invariant. It gives nice is compatible with the group structure, and it also has nice properties with respect to the topological structure, namely with respect to open sets and closed sets. So, with that we conclude our analysis of Lebesgue measure and Lebesgue measurable sets. In the next lecture, we will start looking at functions on measurable spaces and their properties. So, thank you very much.